Okay, welcome back to our discussion on the chemical atomic structure fundamentals, that handout that I gave you. And I'm going to go over a couple of key points here for you, and then try to finish some of this stuff up if possible. So let's see. All right, I want to start off with a couple of key points here with respect to the atomic structure fundamentals. This is going to be, by the way, the video will be 1A. We started 1 last time. We'll continue through all this on a 1 basis, and then A, B, and C, whatever it takes. Okay, so a couple of things. Ions are important because it's going to deal in a non-net neutral charge of atoms, because normally they're neutral charge because protons, positive, electrons, negative, equal each other, and so the net charge would be 0. But that's not always the case. They don't always have to be net neutral charge. And the number of electrons can either be increased or decreased. And of course, the number of protons remains or stays the same because that's basically the identifier of that element. But ions are atoms that are no longer neutral. In other words, net non-zero. They have a varying charge. And they give them two names. First name, the net positive ions, which are basically electron deficient, are called cations. And you can remember them, positive meaning a plus, and there's a sort of a plus right here, cations. Whereas a net negative ion are atoms that are electron rich, all right? And these are called anions. Okay. So, let's talk now about, and this deals very much in ionic bonding, which we'll try to get to later today if possible. Let's talk about what the atomic number is, because that's the key number in all of these elements. For instance, iron, going back to iron, its atomic number, or what we also call a proton number, is the same thing, is 26. We talked about sodium earlier. It has an atomic number of 11. So the atomic number is the number of protons in that atom, and it is what makes that chemical element unique, okay? It is basically what defines that element by its proton number. It's how elements are defined or identified and how they are arranged in the periodic table, okay? It's kind of like their social security number. I mean, every element has a different atomic number, and only that element has that atomic number. So it's kind of the identifier of those elements, the atomic number, or what we also referred to as the proton number. So those are a couple of key things, key terms that I wanted to get across to you. Those are on this handout that I have given you electronically vis-a-vis the email. But I want to go over these arrangement of the electrons a little bit in more detail with you. So let me focus in on that for you right quick. And kind of move this around so we can get all of that in there. Okay, I think I got it. Okay, so let's talk about, and these are what we were talking about earlier with respect to electron configurations. And electrons occupy shells. We talked about those 1 through 7. And each shell then is comprised of these subshells, which are S, P, D, and F. And those are all varying energy levels. And these all hold specific numbers of electrons based upon the number of orbitals in each subshell. And as we said before, the maximum number of electrons per orbital or shell is only 2. And the orbital has a very discrete energy level, as I showed you on that last board before we moved on to this one. And so these are increasing from S to F. So we have subshell S, 1 orbital, 2 electrons, 2 total. Then we have P, 3 orbitals, 2 electrons equals 6. And then we're moving on to D, which has 5 orbitals, again only 2, so that's 10 total electrons. And then F, 7 orbitals times 2, of course, is 14. So, and remember, these are all different varying energy levels, where we had to actually go, when we're in that 3, we had to go to 4s and then 3d, because this D on the 4 subshell was smaller energy level than the 3D. So, at any rate, the basic electron configurations, again, as we said, the first shell, which is quantum, known as the quantum numbers 1 through 7, also have a letter designation, and the first one is K. And again, this is just to review what we said, but again, it's the first shell 1 is 2, and then the next shell 2 is 8 possible electrons, because it goes up to 2p, and then the third shell goes all the way up to 3d, so we have 18 there, because D has a total of 10, so 10 plus 8 is 18. And then shells 4 through 7, they go all the way up to F, okay? And so you could have, something with shell 4, and then 5, 6, 7, and that's how they get these ones with very, very high atomic numbers in them. Okay, so that's the basic structure of those electron configurations. And just as a general rule, as we said before, each shell is more stable when it's full. So they're all trying to achieve that stability of having a full outer shell, or those valence electrons being completely full, meaning they would be like the noble gases on the far right-hand side, completely full, inert, not capable of bonding with anything. All right. And the shells when the shells that are more than half full tend to gain or accept more electrons, and that's where we're going to discuss something known as electronegativity here just shortly. And shells that are less than half full tend to give up or lose electrons. Okay, again, this all hinged around the term of electronegativity, and I'll show you that on the periodic table of elements here in just a moment. So this is the electronegativity, which is the tendency of an atom to gain electron, okay, to attract different electrons. That's what electronegativity is all about, the tendency to attract or to gain electrons. And you'll see where they are located and how they vary on the periodic table of elements here in a minute. Okay, the number of electrons that an atom wants to gain or lose is what we call its valence or its valency, okay? And again, that's those only electrons in that outermost shell are capable of being in that area, and so that's what they call valence or valency electrons. It's only the outermost electrons that are capable of participating in a bonding. And valence electrons are those in the outer shells that can participate in the forming of chemical bonds with other atoms. Those, as I just said, that's what they're all about. It's just those outer electrons are capable of doing that. Okay, so let's move this out of the way, and then let's take this board away and substitute it with the next board, which is all about the periodic table of elements. So make sure I get this all lined up and go back to full frame view here. And let me get this lined up as best I can. All right, I think I got it all in there. Okay. Stop the wobbling. Okay, so this is going to be our discussion regarding the periodic table of elements. Now, this is obviously the tool, the workhorse, as you can see here, what this looks like. And I'll go over this in just a minute. but this give you a little background. There have been many ways in the very beginnings, 1600s, 1700s. It wasn't until around 1869 or so that the Russian scientist Dmitri Mendeleev, and you'll see the spellings of his name many different ways, depending on what dialect you're in. But Mendeleev is really known as the father of the periodic table elements. He was the first one to actually kind of categorize these elements, and in doing so would leave blank spaces, knowing that they hadn't really identified all the elements that were possibly out there. And so that was a big breakthrough in the development of this periodic table of elements. Now, he developed what he called the periodic law, which basically he said that the properties of the elements vary periodically with their atomic mass. Okay, so that's why they call it periodic table. They vary periodically, but he initially said it was vis-a-vis their atomic mass. Later on, it got changed from the atomic mass to what it is now in its protons, or the atomic number. They're arranged now by the atomic number. But at any rate, Mendeleev is one credited with developing the whole structure of this periodic table of elements. Okay, now, and again, this is again going to be 1B here, whiteboard lecture. So it's continuing on with our chemical structures. Okay, so every element is defined by its atomic number, or what we're calling the proton number. It is the chemical's identity number. It is fixed by the number of protons. Okay, and again, only that element has that atomic number. As I said before, it's kind of like their social security number. Now, basically, metals are to the left and center on this table, and non-metals are basically to the right. Okay. Now, there's two groupings here, and we need to know kind of what they're based, because this is how this whole table was developed. But they have periods and groups, and the periods are the horizontal rows, and there's 7 of those rows, and they're in order from left to right by their atomic number. Now, again, that is developing that energy levels as we go from left to right. Okay, and the same number of atomic orbitals in these periods, the same number of atomic orbitals are in each row or shells. So, for instance, if you go through here, if you go down through this table, you can see that here they are 1, 2, 3, 4, 5, 6, 7. If you look through here and look at that outermost shell, you'll see that the same number of atomic orbitals are in that same row. So this would be 1, the 2s, the 3s, the 4s, and on like that. So that's how the horizontal rows are arranged by the number of atomic orbitals in each row. Okay, now let's talk about the vertical columns. All right, the vertical columns are what we know as the groups. All right, these vertical columns. Now they happen to be arranged by the same number of electrons in their valence shell, which is again that outermost orbital shell. That's why they call it the valence electrons. They're all arranged by that, the number of electrons in that outermost shell, or what we call valence electrons. And they represent, these all have similar electron configurations, and the similarities are in both their physical and chemical properties. And they can be stated that the valence electrons basically determines the chemical properties of that element. Okay, so it's important to understand how these periods and groups work together in the formation and the groupings and the arrangements of these elements in this periodic table. Now, let's go back. Electronegativity, again, is that tendency of an atom to attract other electrons. Generally speaking, electronegativity increases from left to right and also from bottom to top. Okay, so let me kind of draw this up here. Let me erase this. I'm going to kind of draw a sketch here of the periodic table of elements. Let's see. Okay. And of course, I'm not going to draw the whole table, but basically, we have something that looks like this with, something, with all the various and sundry groups and rows, etc., etc., etc. Okay, this is just generally speaking as far as what electronegativity is about. Electronegativity. Okay. All right. Let's look at the values there. The elements, again, more to the left, have smaller electronegativities. Smaller electronegativities. All right, and the ones to the right have larger electronegativities. Okay, and so large values have a tendency to acquire electrons. Okay, so they have a tendency to acquire electrons over here. Now, let's look at this from this perspective. The smaller electronegativity elements onto this left-hand side, these basically are the electropositive, which we know again as cations. And these readily give up electrons, okay, and become these cations, okay. Whereas on this other side, more tendency to the right-hand side, these are electronegative elements, and these, of course, are the anions. All right, the anions, and they readily acquire electrons and become, obviously, the anions, and these obviously become the cations. Okay, so now, and obviously these ions are where atoms that the electrons do not equal the protons. In the ions, the number of electrons does not equal the number of protons. Okay, so and they vary. So at any rate, that's what this is essentially about as far as the periodic table of elements. Now let me put this back up here. This is a very unique. There goes the timer. But I want to show this to you right quick, if I can, because this is a really good chart, because it shows more than just the elements, atomic number and atomic masses, etc. But it actually, if you look down here, it shows the actual valence shell configuration on all these elements down here on the right-hand side. Okay, which is really sort of an advantage to see what this is. To actually show, most periodic table elements don't show this, but that's a really unique benefit to this particular table. Also, you see this up here. This is the actual crystallographic structure of that element, and we're going to be talking about those here in the next day or so, and you'll see this designation here being a hexagonal type crystalline structure, and those are categorized down here of what they actually are. Okay, and the ones we're going to be concentrating on, these crystallographic structures, will be the cubic, both face-centered and cubic body-centered crystalline structures. Okay, these two. And if you look real closely, for instance, if you look at iron again, you'll see that it's a body-centered crystalline structure here. So this is a really nice periodic table of elements to be able to look through and understand a little bit more about what these elements represent. Okay, and it's also quite handy as a placemat for your morning breakfast. So, at any rate, okay, we'll finish this up on the next presentation, talking about the atomic bonding methods, and we'll finish that up and move on to crystallographic structures. Okay.